the lights off. Give you better contrast, but then it's too dark now. Maybe actually open up this window. Or how is that? Too dark? Let's try this. Come on. Oh, there we go. Oh, we'll see how it works. Okay, so did you all check out the homework number 1? Did you see that? Okay. Should be a relatively simple MATLAB exercise, right? The related thing are the TA's office hours. So the recitation will be there as usual, but I think now it will have a little different purpose. So the way I see it is like the TA office hours and the recitation, they serve mainly the one purpose, and that is if you need some hands-on help, like bring a laptop and show, hey, why is this not working in MATLAB? So this I think the right place to get your help if you are stuck with homework. If it's something like that you can just formulate this as a textual question, then you can just immediately post it to PSI. If you are like maybe like the assignment did not make sense or you did not understand something, that's just, you can just post it there. But if you need some hands-on help, show somebody something, that's the office hours are good for that. The TAs will be more hands-on with the homeworks. You can of course use also my office hours, but then but maybe better for like something you did not understand about a lecture or something like that, because the TAs will then be also grading the homeworks as usual, so they will be well aware of them. Okay. Did you have any questions about the homeworks or stuff? All good? It's quite a few of you. So I hope everybody is fine. Okay. Huh? Oh, that's right. Yeah, you guys participated in PanApps? Yeah. Wow. That is true. Cool. All right. So let me again quickly recap what we did the last time. So again, like if you only want to remember one thing from the last lecture, then remember the matrix vector multiplication and matrix multiplication, right? So let me just recap it real quickly. So matrix vector multiplication, so for some matrix A and some for matrix and vector V, where I assume that the V is like a column vector. Sometimes I like give it like a little arrow to make it clear it's a vector. And the matrix can be generally a rectangular matrix, m by n matrix, and the vector, it's a column vector of dimension. So sometimes I read like n by 1. You can also look at column vector, and that's also how it works in MATLAB, as just a matrix with one column or one row, right? And that's a special case of a vector. Special case of a matrix, which is a vector. I think that's clear, right? So the matrix vector product, I told you should remember not the formula for how the elements of the resulting vector W, which is, what dimension is it? Very simple question. It's almost m by 1, yeah. Can you read it well? I think it's pretty readable, isn't it? If there is something unclear, then just yell at me. So the matrix is a table of numbers with elements like this. This is very important, so remember it, remind it one more time. And this is a M1, because there was M rows, M2 up to a Mn. So this is like a graphical look at the matrix. Now here my vector V is a column, so it goes V1, V2, and so on up to Vn. Let's get these right. And the result is a vector of W's, W1, W2, and so on up to Wm. Right? And what I would like you to remember is how these W's are computed if I already know these A's and V's. So do you remember it? Can you tell me that quickly? So this is a matrix vector product. I know the matrix, I know the vector. I'm just recapitulating what we did the last time, the most important thing. And I want to compute the W, the matrix vector product, which is another vector of different dimensions. So this matrix is mapping from m-dimensional real vector space to n-dimensional. Sorry, the other way around. From n-dimensional to m-dimensional. See, you always have to think carefully. Yeah. So how do I get the W's? Yeah.
It's the sum of each part of the vector multiplied by each row.
Right. So instead of a sum, you can just say it's a dot product. So I take every row of the matrix and I dot it with V. And that gives me one component, WWI. So yeah, you are absolutely right. It's also the sum over all the elements. So it would be A11 times V1, A12 times V2, plus and so on up to plus A1n times Vn. And that's my W1. For W2, I repeat the same thing except for the second row and so on. So you can look, if you are looking at this as row vectors, this is just a dot product of the first row vector with V, that's my W1. My W2 is dot product of the second row vector with V, that's W2, and so on up to Wm. That's the dot product of the last row of the matrix times my vector V. And now a matrix, so yeah, the matrix doesn't have to have this shape, right? The matrix can also be square. Then it's nice, because if it's square matrix, then I don't have to make a difference between the m and n, right? Then graphically it looks like this. I will not write the actual elements here anymore. You can just imagine there are some numbers there. I'm just trying to give you a graphical idea of the dimensions. The matrix could also be, this is sometimes called the short and fat matrix. The matrix can also be tall and slim, like this, right? That's totally fine. So in this case, m would be more than n, right? Like m would be 20 and n would be 10 in this case. More rows than columns. In this example, it looked like it had like more columns than rows. It's perfectly fine to have it like this. The only thing I need to be careful is that this vector is as long as the length of the vector dimension of the vector has to be the same as the number of columns, and gives me this, right? Sort of good to have like a mental picture of these operations so you can get the types. And for a matrix multiplication, so if I have matrices A times B, and the dimension of A is again m times n, and the dimension of B cannot be arbitrary, it has to be n times k, right? So these n's have to be the same thing. The focus is not as good as, that's better, right? Just trying to mess with the autofocus so it's not refocusing. So that was annoying, but no. So matrix product. So it gives me another matrix C of dimension, what dimension would it be? M times k. That's right. Like the n disappears here and I just get the outer dimension. And the maybe the easiest way you can look at it is if I look at it as matrix vector product applied to all columns of B. So if my matrix B is an n by k matrix, that means that I can also look at it as like a stack of this B of individual columns, right? So B1 to Bk. So this is like my B matrix. And then the product C is nothing but matrix vector product for all the columns individually. So AB1 and so on to ABK. And that's my matrix C. That's the easiest way you can remember how matrix product is defined. So if you only wanted to remember one thing from the last lecture, remember these two things, the matrix vector product and matrix product. Maybe I'll remind one more time that what it means geometrically is that the matrix is represents some linear transformation with respect to two chosen bases. This is actually. Do you have any questions to what we talked about last week? Because you are still taking notes. I was hopeful that you wouldn't have to, but you know what's actually even better than taking notes during the class is like after the class, if you like try to like basically do these things but by yourself. Basically actually try to like do some thinking on the paper. If you really want to remember things, like try to really like draw these things, not just like copying. That's not gonna give you much insight. But if you like will try to like figure it out with the paper, that usually works much better for some reasons I don't understand completely. Okay, so this is like a quick summary. So linear transformations. So if I take arbitrary linear transformation, what it is, it maps one finite dimensional vector space onto another finite dimensional vector space. Most of the vector spaces we are dealing with are finite dimensional, right? We had some examples of vector spaces that would not be finite dimensional, like all the functions on the real line or on some interval. But all these R2n, they are finite dimensional. So for these, you can construct a matrix that represents the linear transformation with respect to two chosen bases. So if one vector space, you choose a basis there. Second vector space, maybe like this. V1 maps to V2. I have there a basis, I guess, I don't know. B1, basis B2. It's like a collection of vectors there. And with respect to these two bases, I can write the matrix that maps from V1 to V2. So that's what it is. So in the following, we will look at some very important special examples of linear transformations, starting with the simplest one, rotations in the plane. Well, simplest. It already gets interesting there. So let's take a look at it. Maybe I could do this. So I'm looking at so we are in the plane. That means vector space R2, and I take an arbitrary vector xy, and I want to rotate this about the origin by angle theta. So we could show geometrically that it's a linear transformation. So again, let's recall the definition. What does it mean for a transformation to be linear transformation? So when I was writing this f from V1 to V2, that doesn't mean necessarily it has to be linear transformation, right? What linear transformation needs to, it has to be this type, but has to satisfy the property of the linearity property, right? It has to satisfy that it doesn't matter if I first sum the two vectors and then transform, or if I first transform and then sum, right? And this is the same thing for scalar multiplication. So for rotation, I could like do it geometrically or prove it just from the concept of rotation. But this will be the fact that rotation is a linear transformation will be obvious from the following, because we derive its matrix representation, and once we have the matrix representation from that, it's clear it's linear, right? Because if the transformation is defined by the matrix, then the linearity follows easily. So the one thing we talked about last week is that the complete action, the complete picture, the complete understanding of the linear transformation is obtained by understanding what does it do on basis vectors. So if we pick in R2 the standard basis vectors, the E1 and E2 basis vectors, all we need to worry about is where the rotation r theta, where theta is the angle of rotation, maps these two vectors. And this we can find out relatively easily by like basic trigonometry, I guess, right? So should know that if I have like a unit circle, so it's supposed to be a circle, and so this is an edge of length 1, and here is angle theta, then can you see this there? What am I drawing? So the length of this thing is what from basic trigonometry? It's also written there, but So if this is 1 and I have a triangle like this, the length of this edge is cosine of theta. So this is cosine of theta. And the length of this edge, meaning this coordinate here, that's going to be the sine of theta. For arbitrary angle theta, right? So this immediately tells me where the vector 1, 0 maps to by the rotation, right? Because vector 1, 0, that's this guy here. Here is my 1, so this is 1, 0. And if I rotate it by angle theta, I rotate it to this vector, and it has coordinates cosine theta and sine theta, right? So this is my first column of the matrix, cosine theta, sine theta. So you should be getting like the idea that in matrices we often think columns, and when matrices are composed, we are going from right to left. Maybe that's also something that I should highlight. That's definitely worth remembering from the last week, that if you are composing matrices, you have to parse it from right to left, even though you may be used to reading from left to right. What about the vector 0, 1? So that's this vector, right? So where does that one map? We could look at it geometrically the other way. We can do it. We can just say that this is a rotation of 1, 0, but by theta plus 90 degrees. So, and you probably know these formulas, that cosine 90 degrees plus theta is minus sine theta, and sine of 90 degrees plus theta is the cosine of theta. That's like one way you could look at it. That if I rotate my 1, 0 not by theta but by theta plus 90 degrees, then it's the same thing as if I rotated the vector 0, 1, which is here, by angle theta, and I get, maybe this here it's a little better visible. So this is exactly my sine, except now it's with minus, and here is the thing that was cosine. So 1, 0 maps to cosine theta, sine theta, and 0, 1 maps to minus sine theta, cosine theta. So now what we have here is the matrix of the 2D rotation by angle theta. Everybody agrees? All you really need to know is this basic trigonometry. So if I have a right triangle, this side is length 1, that you need to know that this length is cosine and this length is sine. And from this, this can be derived just by simply looking at it geometrically. You can immediately notice interesting thing about these two vectors. Do you immediately notice it? There is actually a number of interesting things. So we will look at it on the next slide. Is this clear? The very basics of rotation. So rotation is a very important example of a linear transformation. It's given by this matrix. And rotation matrices are fairly special. So the things I wanted you to notice is, so the first thing you can immediately notice is that these two vectors are orthogonal. Do you remember what it meant to be orthogonal? If I compute the dot product of the two columns of this matrix, what do I get? So this is one vector here, this is another vector here. If I do their dot product, it's sort of interesting, right? What happens? I get 0, right? Because I get cosine theta, sine theta with minus, and there's the same thing without the minus, so it just cancels out. So that means that these two vectors, when I look at them, they have angle 90 degrees. That's what we talked about when we discussed dot product, right? And that's called orthogonal. It was from the previous slide. You can clearly see it here, right? This is cosine theta, sine theta. This is minus sine theta, cosine theta. So this angle here is exactly 90 degrees. Yeah. There is one more interesting thing about this matrix. It's written further down here, but let's just look at one of these vectors. Let's look at the first one, the cosine theta and sine theta. It's another funny thing, because you might remember this trigonometric identity, that cosine theta squared plus sine theta squared is 1, no matter what the theta was. Do you remember that from trigonometry? So what that means is that the length of the first vector is 1, so it's a unit vector. Now guess what? The same thing applies to the second vector, right? Because the minus here doesn't matter when I square it, so I again have sine squared plus cosine squared, that is 1. So let me summarize that. So the columns of the matrix, turns out that the rows as well, right? They have unit length and they are orthogonal to each other. We will see that this will be true not just for 2-dimensional rotations, but for rotations in any dimension. 3-dimensional, 4-dimensional, and so on rotations. But here we are looking just at the 2D case. And matrices with this property, we call them orthonormal matrices. So what does it mean for a matrix to be orthonormal? I think we will talk about it a little more detail later. But it means that if I look at the individual column vectors of the matrix, as I always was, then if I pick any two of the columns, that they are orthogonal vectors, and every single of these columns is a unit vector. At this, for 2x2 case, it's written here. So this is the first column of the matrix, the ux. This is the second column of the matrix, uy. So I could also say that r theta is ux and uy. And I'm putting this little hat there to highlight that this is a unit vector. And so the vectors are unit and their dot product is 0, meaning they are orthogonal. Okay? This is a very important property of rotation matrices, that they preserve the length of vectors and the angle between vectors. So let's take a look. If I have two vectors, so one vector A, B, and C, D, I'm still in the plane, and I transform both of them, I rotate all of them by rotation with angle theta. Not as sharp as I wish this to be sharp. Huh, weird. Yeah, there's something funny going on, just let me, please. So what I'm looking at, so I have two vectors, A, B, and C, D. They have some dot product, right? I can compute their dot product. And I want to see what changes if I rotate the whole thing by angle theta. So I rotate the first vector by theta, and I rotate the second vector by theta. So let's just compute it. So it's a linear, rotation is a linear transformation, just like any other, right? So to find its value, to find the result, to compute the linear transformation, all I need to do is to do the linear combination of the transformations of the basis vectors, right? Those are the columns. So I compute AUX plus BUY. The same thing for the second one, so CUX plus DUY, and I do the dot product between the two, right? Now we know that the dot product has a number of useful algebraic properties, like the distributivity. So that means that I can go, with the dot product, I can go inside. That's the distributivity. I use both the, with respect to vector addition as well as with respect to scale multiplication. So which lets me to rewrite it like this. So what happened here is the UX with UX dot product. Here is UX with UY. UY with UX and UY with UY. Now what happens next is we already established that the UX are unit length, right? So UX dot UX is 1, right? Maybe I'll write it here. So UX by UX is 1. UX by UI is what? 0, exactly. The same thing applies, of course, for UI by UX, because it's the same thing as UX dot UI, also 0. And UI by UI is the same thing as here, that's 1, right? So what I end up with is AC plus BD. These things went away because they were multiplied by 0. These were multiplied by 1. And it's the same thing as the dot product of AB and CD. So what it means we have just proven this following like lemma, I guess, or something, that if I pick arbitrary 2 vectors in R2 and I rotate both of them by the same rotation, has to be the same rotation, then the dot product doesn't change. In other words, rotation preserves angles, right? If I had some vectors u and v, they don't have to be unit, they don't have to be anything. There's some u and v, and I rotate the entire thing. Look, I could like rotate it like here. And if I compute the dot product of the rotated, maybe this wasn't a great idea, of the rotated u and rotated v, this angle will not change. It's sort of obvious if you think about it geometrically, but here we have like a hard algebraic proof, right? Sometimes the intuition cannot be sufficient, right? If you'll be thinking about rotations in 4 dimensions, there you cannot really like easily imagine what it means to like just like rotate the vectors, and you have to rely on these hard calculations. The same, so if we preserve angles, that means we also automatically preserve lengths, right? Is there a question? No? Because length is just a special case when I use the same vector on both sides. So it's u dot u, the square root of that would be the length, the Euclidean norm. So because it preserves the dot product, it preserves both the angles and the length. Obviously, rotation, if I rotate a vector, it does not change its length. And here is like a proof that is true. Okay? So rotations are cool. You might be thinking, what about translation, right? I don't know if you took already some graphics classes. Some of you probably did, right? But like in graphics, this is what you usually start with, like this basic transformation, translation, rotations. Translation is like probably the simplest operation you can think about, right? All it really is just like adding a constant vector. That's all that translation is. And there is a catch, because translation is not a linear transformation. So let me try to explain it a little bit slower. So translation is also like an operator. So if I'm in R2, it's a transformation from R2 to R2. So the type is the same as of a linear transformation. It takes an R2 vector, some x, y coordinates, and returns some x prime, 1 y prime, which are translated, right? And the only thing it does, it adds a constant vector t. T would be some dx, dy, the translation in the x and y coordinates. Now, if you think about it, translation really has no chance to be a linear transformation, right? Because what is true for all linear transformations? So I can take any linear transformation and I can represent it by a matrix, right? So if I'm in R2n to R2n, it would be an n by n matrix, and we have some numbers in it, right? It doesn't really matter what numbers are there, because if I multiply it by the origin is a 0 vector, right, in arbitrary dimension. In R2 it's just 0, 0, in R3 it's 0, 0, 0, and so on. No matter what is in the matrix, I always get zeros back, right? Because everything is multiplied by 0, I have to get 0 vector back, right? So every linear transformation has to map 0 to 0. That's also true if I have a linear transformation from v1 to v2, so they are different vector spaces. Then it would be like a rectangular matrix, right? But again, if I just hit it with zeros, I have to get zeros back, right? So there's no way how we could model translation directly just with a plain vanilla linear transformation, right? Here is like another, like I guess, more mathematical way to look at it. Because for linear transformation, we would have to verify this property, right? We would have to look what does it do on alpha v plus beta w. Well, what does translation do? It just adds the t, right? But that's different from applying t to v, because t on v would be v plus t, right? T on w would be w plus t. And now if I take this okay, I'll write it all. T alpha TV plus beta TW, I get this, and that's clearly not the same thing, right? Here I have T times alpha plus beta, and you have just one T, and that would have to be true for all alpha and beta, so that can't be right. I think this is a little more intuitive. Why? Because 0 has to be mapped to 0, so we have really no way of translating just by a linear transformation. So do you know what is the way around this? Because we need translations, right? We wouldn't get really very far in graphics or robotics, or if we could only do rotations. I mean, somewhere rotations are really all you care about, where the global shift has been already taken care of. Have you heard it somewhere, how to deal with translation? There's a very cool trick. So mathematically, it's called affine spaces and affine transformations. It's also instructed to give you like a little bit of a perspective. Like right now, it might seem to you that like all transformations are, it's again blurry. But all transformations are linear transformations, right? But affine transformation is another example of a transformation from V1 to V2. In this case, it's not linear, so it does not satisfy this property. But it satisfies a different property. So a transformation is affine if the transformation minus its action on the 0, on the origin, is linear transformation. So this is how affine transformation is defined. So this is like a different kind of mapping than linear transformation, because we know that linear transformations have to map 0 to 0, as opposed to affine transformations which can map 0 to something non-zero. And this is really how we capture it. So we say that, okay, we allow it to map 0 to somewhere else, but then with respect to that point, it has to be a linear transformation. So basically, a affine transformation, you can think about it as a linear transformation plus translation. I allow the transformation to translate the 0 somewhere else, and after it's done with translating the 0, the rest can be only linear transformation. It'll be a little clearer when we get to the projective plane and how to represent it using matrices. That's where we are trying to get now. How to represent both linear and affine transformations elegantly using matrices. That's the basic building block in both robotics and computer graphics and computer vision. It's very useful. So in general, this is called coordinate transformations. I guess, like for example, in vision, so I'm not always giving just graphics examples. The pitch is that I always have some coordinate systems with respect to them. I'm taking the measurements of the real world. So for example, if I had like a camera, I could define a coordinate system associated with the camera, so some origin and x, y, and z coordinates, and I could just type with the camera and it would be my coordinate system of a camera. In robotics, I might define a coordinate system associated with like some link of a robot or a joint of a robot. And the coordinate transformations or coordinate systems are basically what we call bases in linear space, except that when we talk about coordinate systems or frames of reference, they can also translate. I guess that will be a little clearer from the following. So right now, we have seen a special feature of the rotation is that it preserves angles and distances, right? The translation is very easy to realize that the same is true for translation. If I just translate two vectors somewhere, The angle between them stays the same, and their lengths also are unchanged. So both translation and rotation are called rigid transformations. That's because if I take a rigid body, like this pen, for example, all transformations it can undergo are rigid transformations, right? If it's not deformable object, then all it can do are rigid transformations. There are, of course, other basic linear transformations like scaling and shearing, which are perfect. Like scaling, for example, is a perfect linear transformation, right? What would be this matrix corresponding to? This would be like a scale in the x-axis by 2, right? And keeping the y-axis intact. And it's a perfect linear transformation, but it's not rigid, right? That would, if I like applied it, if we were in 3D I would just do this, right? I would just do, if I apply this transformation to my pen, that would mean that in one dimension it would grow by a factor of 2, right? So chances are I cannot do it to like a rigid object like that, right? Maybe I can like bend it a little bit, but certainly not stretch it by a factor of 2. So that's why rigid transformations are quite different from the other transformations we cannot really apply to rigid objects. What is cool and maybe not completely trivial is that any transformation of a rigid body can be expressed as a composition of a translation and a rotation. So if I have a rigid object like this pen, and no matter what I do to it, I move it from one position to another one, I can always find a translation and rotation that will perform this motion, that will be equivalent to doing that motion. It's actually sort of cool to show this in 2D. Let me show you a 2D example. I'll actually also explain a little bit the coordinate systems. So let's say I have this plane, and I have some point in the plane, and I want to find the coordinates of the point. Right? So I define a coordinate system somewhere, like if I had some special origin thing here, maybe I had like a camera here, or maybe I would have like a base here or something like that. So this would be one coordinate system with respect to which I can find the coordinates of this point. And how would I find them? I would just form this vector. I would assume that this is my 0. I'd find this vector and look at what are these coordinates. This would be my x coordinate and my y coordinate, right? So what I wanted to show you here was if I take one coordinate system like this and I subject it to a rigid body transformation. So I translate it and rotate it. So let's say I'd like translate the origin here and I rotate it like this. So this would be, I don't know, axis x1 and y1. This would be x2 and y2. There would be some point 1 and point 2, right? So now I have like two frames. One frame would be p1, x1, y1. And the second one would be p2 and x2 and y2. In those affine spaces, sometimes we make a difference between points and vectors. The vectors are the objects from the linear or vector space, and points are what lives in affine space. It's like the difference is mostly semantics. So what I wanted to show you here is that if this could also be some rigid object, right? Some rigid object here, and this is the same rigid object modified by translating and rotating it. Now the cool thing is that in plane, if I'm in R2, then any rigid body transformation is either a pure rotation or pure translation. That's sort of cool, actually. You can be thinking how this could be a pure rotation, right? Because I obviously translated it, right? The trick is that I can rotate about an arbitrary point in this space. And if I pick the point correctly, I can just rotate from here to there, right? So if I could find a point, so let's see. So I will do this. and bisect it. And I will take these 2 points, find the line between them, and again bisect it. And these 2 lines will meet somewhere, and somewhere around here would be the center of rotation. So now look at this. If I take this coordinate system and I rotate it about this point by the right angle, I will arrive right there. Do you see that? So this relative motion I can describe as a pure rotation if I pick the center of rotation right. I can also describe it as a rotation and translate. Like if I pick the center of rotation here, right, I can first rotate, do this rotation, and then translate, right? That's also, and I will get the same result. But the cool thing is that in plane, any rigid body transformation will be either pure rotation. That's the case if I either pure translation. That's the case if I just translate, right? If it's really just moved to the right by 2 or 3, then I clearly cannot rotate it there. But the moment I have some rotation that's different from 0 and 180 degrees, then I can find the center of rotation that will just rotate it right there. So the translation will sort of disappear by carefully choosing rotation center. That's something non-trivial actually. Like this you could think about it also like rotating about a point at infinity. But I think I'm going a little bit too crazy here. But this actually is important, like in robotics, for example. Speaking of robotics, I have this slide which shows coordinate transformations in robotics. This is some PR2 robot. And so what a robot is and how a robot is modeled in robotics is as a collection of rigid bodies which are connected by some movable links, right? So each of these pieces is a rigid body, and the rigid bodies, they can move relative to each other, right? So it's not quite like human, that's like a little bit squishy and like some muscles and things like that. The robot can have only much simpler motion, like the joints are typically just like rotational or translational, either like the most common ones are really just rotating about a single axis, right? I think like hinge joint. I think that's what this robot has the most. So a robot is basically nothing. That's why the rigid transformations are so important, right? Because it's a collection of rigid bodies. So in each of these links, I can define a rigid transformation. And then the rigid transformations, they will be related based on these angles in the joints. You'll actually, your first project, which we will start with as soon as you are done with the homework number 1, will be basically figuring out something like this, how the coordinate doing like a little project, little example, how these coordinate transformations multiply together to create, to compute the composed transformations, for example, from the base to the hand. And don't worry, we'll discuss that here. Actually, right now. Is this clear? Okay, so what I'm slowly getting to is like this, the nice, elegant mathematical way how to describe all coordinate transformations, so both translations and rotations, and also the non-rigid transformations if we need them for some reason. So let's start again. Let's look again at coordinate transformations. So as I said, if I have some point, look at this. If I have some point in plane, like in 3D is the same thing, it's just for didactic purposes, it's easier to explain it in the plane. Normally we'd probably be measuring coordinates of a point in 3D, but here it's just a 2D example. And I can measure the coordinates of the point with respect to different coordinate frames, right? So here is one coordinate frame A and one coordinate frame B. this is important because with respect to frame A, I will get totally different coordinates than with respect to frame B, right? But what is important that these coordinates are related by a coordinate transformation from the frame A to the frame B, right? As I said before, this is really important because the frames A and B, for example, can be frames on two adjacent links of a robot, right? And I need to figure out what is coordinate of some point in space I want to reach to by a robot with respect to different links of the robot. That's like a motivating example. So if I denote the coordinates of point P with respect to the frame A as PA, and the coordinates of the same point, it's still the point P, but now I measure the coordinates with respect to B, I get a vector PB. And PA and PBs are just standard vectors. Now, what I can say is that I have a matrix that represents coordinate, or in general, I guess a function that represents coordinate transformation between these two frames. So let's look at this. So it's a function that takes coordinates with respect to one frame. It takes coordinates with respect to frame A and returns coordinates with respect to frame B. So the GBA takes the PA and returns the PB. So this tells me that this is a matrix that tells me how to convert the coordinates. This is just like a notational thing, that the BA, but it's very useful notation because it sort of makes it like match. The B here is the same as this B, and the A is the same as A. So this basically is like a way to help you remember that it transforms from A to B. Again, you have to be reading it from right to left. So like the GAB should be clear that this is a very different transformation. It's actually the inverse of the transformation, but we haven't really talked about inverse yet. So in the following, I would like to explain in detail how to get these coordinate transformation matrices. And the catch there is that we will have to deal with translation somehow. And translation cannot be directly captured as a linear transformation, so we'll have to do one trick. The trick is called homogeneous coordinates. Have you heard about homogeneous coordinates before in graphics, maybe? Or it really appears everywhere. Vision, graphics, robotics, maybe somewhere else too. It basically is a trick how to handle. That's a little more than a trick. It has a very solid mathematics behind it. But it's a way to handle translation using matrices. Because the nice thing about matrices is that we can compose them using matrix multiplication, right? You could just like have the translation on the side and just sort of like remember, like define some sort of class where it's like a translation part and the linear part. But it's much nicer if we can write it in one matrix, and then we can use all the linear algebra we know so far, just like matrix multiplication, but that already is useful, right? And we can get this done by introducing homogeneous coordinates. I'll just show you. So I don't think I have the time to explain that now, because we have to finish in a little bit. I just want to give you an idea of what is going to follow. I'll give you the spoiler for the next class. The spoiler is that we go from R2 to R3. So if we want to represent all affine transformations from R2 to R2, we do it using 3x3 matrices, using mappings from R3 to R3. And in more details, I will explain on Wednesday. I'll leave you with a little overhang, unless you already know this. Sounds good? Okay. Any questions?